Okay, so we're going to try to heat up our ice from negative 20 to positive 20. The first step we're going to do is heat up the ice from negative 20 to what? 0. Okay. By the way, ice will not exist above 0. You can't have ice at 20 degrees. Or actually, I should say you can't sustain ice at 20 degrees. The ice itself will never be 20 degrees positive or more. Yeah?
So, will that energy change, though, depending on, like, how long you want it to take and, like, how much heat? Like, you're like, oh, I want to turn this into liquid, like, right now, and you put it on, like a pan and you start to boil it. Wouldn't that be more energy than just waiting for it to sit, like...
It will still take the amount, it will still take the same amount of energy, but yeah, how you supply the energy will affect the time. So for example, if you have an ice cube and you just sit it out on the table, it's going to take some time versus putting it on the stove. Now the total amount of energy will be the same whether you just stick it on the table or put it on a stove. But if you supply it quickly, like on a stove, then it's going to go faster. Okay, so we're going to go from negative 20 to positive 20. So let's figure out how much heat it takes to do that. So for this, we're going to be using MC delta T. Okay, so the mass we said was 0.5. Okay, now the C is a C for ice. And the C for ice is different than the C for water. So the C for ice is 2060 joules per kilogram per degree C. Yeah.
Are we ever going to have to deal with it in Kelvin? Like joules per kilograms per Kelvin?
You could, since it's a delta T, like if this was negative 293 to 273. Notice the change is the same.
Okay.
So you could. Okay, and this is what, 20 degree change? So let's see how much energy it takes to heat up the ice. So I could do this. 20, 60, 0. 20,600 joules. All right, now we have ice at 0 degrees. Adding heat is now going to do what to our ice? Melt the ice. So at this point, we're going to melt the ice, and it takes heat to melt it. Okay, so to melt the ice, we have something that's called the heat of fusion. Actually, let's write that. And this is basically the amount of heat needed to melt something. And this would be if you're adding heat, you're going to melt it. What would it happen if you remove the heat? If I remove heat from liquid water, what's going to happen to it? It's going to freeze, yeah. So if you add the heat, we'd say it's melting. If you're going to remove the heat, we're going to freeze it. So depending on what direction you're going, you're either going to add or remove. So anyway, the equation for this is pretty straightforward. It looks like this. Q equals mH F, where m is the mass and then h is a constant. So h is going to be different for different materials. Okay, for water, HF is 3.34 times 10 to the 5th joules per kilogram. Alright, so let's see how much heat it takes to melt this 500 grams of ice. So our mass was 0.5. Our H was 334. Okay, so the amount of heat it takes to melt this, $167,000 joules. Alright, so we now have liquid water. We've melted our ice. What's the temperature of our liquid water? 0 degrees. So if I add some more heat, what am I going to do to that liquid water? I'm going to heat it up. Okay, we're going to heat it up. So that's what we're going to do. We're going to heat up the liquid. Now the liquid will exist from 0 degrees until how much? 100? At which point we've reached our vaporizing point or boiling point. Okay, so we're going to use MC delta T. .5. And now we will use the C. It's in liquid form, so we use the 4180. And we went from 0 to 100, so that's how much of a change?
100.
Okay. What's that? 290? So this is the amount of heat to heat it up from 0 all the way to 100. Alright, we now have liquid water at 100 degrees. What starts happening at 100 degrees? Starts to vaporize or boil, right? Okay, so just like we had before a heat of fusion, we have a heat of vaporization this time. The equation looks exactly the same, except we use QVs instead of QFs. And our H constant is going to be different. So the HV for water. And by the way, these are all different. I mean, if it's steel, it's going to be different. If it's water, if it's gold, they're all different. So the HV for water is 2.26 times 10 to the 6. And again, this is the amount of heat needed to boil away the water. So if you had a pot of water, you leave it on your stove and it boils away, that's how much heat you must have added. Okay, so our mass was 0.5. We just plug in our 226, 10 to the 6. So a little over 1 million. Okay, we vaporized all our water. What is our, it's in steam form now. How hot is our steam? 100 degrees. So what do I want to get it up to? 120. So we're going to heat up the steam from 100 to to 120. Which equation are we going to use? Are we going to use one of the MH's or one of the MC delta T's? Delta T. So you always use the delta T when you're changing temperature and use the MH when you're changing the phase. Alright, so our mass was 0.5. Now C for steam is going to be different than liquid or ice. So C for steam, it's almost the same as the ice. It's 2020. And the change again is 100 to 120. That's a 20-degree change. Okay, so what was the original question? So what are we going to do now? Add them all up. So you have to figure out how much heat for each of those various steps, and then to find the total, you're going to add them up. All right. Sorry, there's no easier way to do it. You have to look at each step individually. It's like 1,500,000 or something. How much? Someone help me out. $1,540,000. $800? Yes? Confirmed? Okay. What's the dominating factor, by the way, when you look at all these? What's the takes the most energy to use?
Water.
Heating up the water? No.
Vaporization.
Boiling, the vaporization. Yeah, notice that took like 2/3. 2/3 of our energy came from just vaporizing. It takes a lot of energy to change from a liquid into a gas.